A matrix is simply a rectangular grid of numbers or symbols arranged in rows and columns, much like the cells of a spreadsheet or the seats in a theater. Each row is a horizontal line of seats, each column a vertical line. The order of a matrix tells us how many rows, m, and how many columns, and it has written as m times n. For the matrix A equals a 2 by 3 matrix with entries 1, 2, 3 in the first row and 4, 5, 6 in the second row. There are 2 horizontal lines, rows, and 3 vertical lines, columns, so we say A is of order 2 by 3. In engineering, such an arrangement can represent a set of measurements taken at different locations. Rows over several time instants, columns, or a small image where each entry is a pixel intensity. The order immediately tells you the size of the data set you are dealing with, which is fundamental for any further calculations such as addition, multiplication, or solving linear equations. Explanation: matrices come in many shapes, and the shape often tells you how they can be used. Square matrix, same number of rows and columns, n by n. Think of a square chessboard. Each position has a partner both horizontally and vertically. Example: B equals a matrix with entries 7, 8 on the first row and 9, 10 on the second row. It has order 2 by 2. Rectangular matrix. Rows and columns differ. M not equal to n. It is like a rectangular table where the number of seats on each side is not the same. The earlier A is a rectangular matrix with 2 rows and 3 columns. Row matrix, only one row, 1 by n. Imagine a single horizontal list, such as a schedule of tasks for one day. C equals a matrix with a single row containing 1, 2, 3. Column matrix, only one column, m by 1. This is a vertical list, similar to a shopping list written top to bottom. D equals a matrix with a single column containing 4, 5, 6. These simple forms are useful as building blocks. For instance, a column matrix can represent a vector of forces acting on a point, while a row matrix can hold coefficients of a polynomial. The key idea is that the order tells you quickly what kind of physical or engineering quantity the matrix may model. Explanation: certain matrices appear again and again because of their special algebraic properties. Zero matrix dash, every entry is 0. It behaves like the number 0 in ordinary arithmetic: adding it to any matrix leaves the other matrix unchanged. Zero matrix for 3 by 3 is a 3 by 3 matrix of all zeros. Identity matrix dash, a square matrix with ones on the main diagonal and zeros elsewhere. It is the multiplicative one for matrices: multiplying any compatible matrix by the identity leaves it unchanged. Identity matrix for 3 is a 3 by 3 matrix with ones on the diagonal and zeros elsewhere. Diagonal matrix dash, only the diagonal entries may be non-zero, all off-diagonal entries are 0. It is a scaled version of the identity where each diagonal entry can be different. Diagonal matrix D has 5, 3, 7 on the diagonal and zeros elsewhere. Scalar matrix dash, a special diagonal matrix where every diagonal entry is the same scalar k. It can be written as k times I. 4 times identity is a 3 by 3 matrix with 4 on the diagonal and zeros elsewhere. In engineering, the identity matrix often appears when you linearize a system of equations around an equilibrium point, while diagonal matrices represent systems where each state variable evolves independently, no coupling. The zero matrix can model a dead or inactive component in a larger model. 3 important symmetry-related classes of square matrices are often used in physics, computer graphics, and control theory. Symmetric matrix, the matrix equals its transpose, A equals a transpose. Geometrically, the entry above the main diagonal mirrors the entry below it, like a mirror placed along the diagonal. Example: S equals a 2 by 2 matrix with entries 2, 3, 3, 5. Symmetric matrices have real eigenvalues and orthogonal eigenvectors, making them ideal for representing energy, stiffness, or covariance in engineering. Skew-symmetric or anti-symmetric matrix, the transpose flips the sign, A equals negative a transpose. The diagonal entries must be 0, and the off-diagonal entries are negatives of each other, like a seesaw balanced at the center. Example: K equals a 2 by 2 matrix with entries 0, negative 4, 4, 0. Such matrices represent rotational operators in 3-dimensional space. The matrix K corresponds to a 90-degree rotation in the plane. Orthogonal matrix, its transpose is its inverse. Q transpose Q equals Q transpose equals identity. The rows and columns are unit vectors that are mutually perpendicular. Orthogonal matrices preserve length and angles, which is why they model pure rotations and reflections in computer graphics and robotics. If Q equals a 2 by 2 matrix with entries 1 over square root 2, 1 over square root 2, negative 1 over square root 2, 1 over square root 2, then one can verify that Q transpose Q equals identity. In engineering, orthogonal transformations keep the physical size of an object unchanged while changing its orientation. Triangular matrices are a convenient way to store systems that have already been simplified, for instance after Gaussian elimination. Upper triangular matrix, all entries below the main diagonal are 0. It looks like a right-angled triangle opening upward. Example. U equals a matrix with rows. First row 1, 2, 3, second row 0, 4, 5, third row 0, 0, 6. Only the entries on and above the diagonal may be non-zero. Lower triangular matrix. All entries above the main diagonal are 0, forming a triangle that opens downward. Example. L equals a matrix with rows. First row 7, 0, 0, second row 8, 9, 0, third row 10, 11, 12. These forms are extremely useful because solving a system UX equals B or LX equals B can be done by simple back substitution or forward substitution without the need for matrix inversion. In structural engineering, after applying the finite element method, you often obtain a stiffness matrix that is symmetric and can be factorized into L and U matrices, LU decomposition, to solve for nodal displacements efficiently. In many practical problems, most of the entries of a matrix are 0. Recognizing this leads to huge savings in storage and computation. Sparse matrix, a matrix in which a large fraction of the entries are 0. For example, a 4 by 4 sparse matrix may look like S equals a matrix with first row 0, 0, 0, 5, second row all zeros, third row 0, 0, 3, 0, fourth row all zeros. Only two non-zero values, 5 and 3, are stored, often in special data structures such as compressed sparse row (CSR) format. Sparse matrices arise in network analysis, adjacency matrices of large graphs, circuit simulation, and finite element discretizations where each node connects only to a few neighbors. Dense matrix, the opposite case, where most entries are non-zero. Dense matrices are common when the data represents a complete set of relationships, such as the covariance matrix of a set of variables with strong interdependence. The distinction matters because algorithms for dense matrices, for example classic Gaussian elimination, have big O of n cubed time complexity, while specialized sparse solvers can reduce both memory and time dramatically, often to big O of n or big O of n log n for certain structured sparsity patterns. A block matrix groups a large matrix into smaller submatrices, blocks, which can be treated as single units. This is analogous to splitting a large spreadsheet into quarters, each quarter being a smaller table that can be worked with independently. Consider the 4 by 4 matrix written in block form. A equals bracket a sub 11, a sub 12, a sub 21, a sub 22 bracket, where each a sub ij is a 2 by 2 matrix. A sub 11 equals a 2 by 2 matrix with 1, 2 in the first row and 3, 4 in the second row. A sub 12 equals a 2 by 2 matrix with 5, 6 in the first row and 7, 8 in the second row. A sub 21 equals a 2 by 2 matrix with 9, 10 in the first row and 11, 12 in the second row. A sub 22 equals a 2 by 2 matrix with 13, 14 in the first row and 15, 16 in the second row. Then the full matrix is obtained by placing those blocks in the appropriate positions. Why use block partitioning? It mirrors the physical decomposition of a system. In a multi-body mechanical model, each body may have its own stiffness submatrix. The global stiffness matrix is assembled from these blocks. It enables the use of the Schur complement and other block matrix formulas to simplify inversion or determinant computation. Computationally, modern software MATLAB and NumPy can operate on blocks in parallel, speeding up large-scale problems. Understanding block structure is essential for advanced topics like model order reduction, control system design, and solving coupled partial differential equations. Find the order of a given matrix. Determine the order of A equals a 3 by 3 matrix with entries 2, 4, 6, 8, 10, 12, 14, 16, 18. Count rows 3 and columns 3. Order equals 3 by 3. Verify symmetry or skew symmetry. Is K equals a 3 by 3 matrix with entries 0, -7, 2, 7, 0, -3, -2, 3, 0 symmetric, skew symmetric, or neither? Compute K transpose. If K transpose equals K, then symmetric. If K transpose equals -K, then skew symmetric. Here K transpose equals -K, so skew symmetric. Determinant of a diagonal matrix. Find determinant of D where D is a diagonal matrix with entries 4, -2, 5. The determinant of a diagonal matrix is the product of its diagonal entries. 4 times -2 times 5 equals -40. Prove orthogonalities. Show that Q equals a 2 by 2 matrix with entries 3/5, 4/5, -4/5, 3/5 is orthogonal. Compute Q transpose. Q transpose equals a matrix with entries 3/5, -4/5, 4/5, 3/5. Multiplying gives the identity matrix. Therefore, Q is orthogonal. Identify a block matrix and write its blocks. Write the 4 by 4 matrix M equals a matrix with rows 1, 0, 2, 3, 0, 1, 4, 5, 6, 7, 8, 0, 9, 10, 0, 11 as a block matrix with 2 by 2 blocks. Partition after the second row and column. M equals block matrix with M11, M12, M21, M22 where M11 equals a 2 by 2 matrix with entries 1, 0, 0, 1. M12 equals a 2 by 2 matrix with entries 2, 3, 4, 5. M21 equals a 2 by 2 matrix with entries 6, 7, 9, 10. M22 equals a 2 by 2 matrix with entries 8, 0, 0, 11.